Welcome to the class. Today we are going to talk about nozzle flow. The reason for the discussion for nozzle flow lies in the fact that we are going to start about the engines and we are going to discuss more about the details and components of the engines. And in case of mainly turbojet engine or in case of ramjet engine, we know that nozzle is one of the parts. Initially air comes into the compressor, it gets compressed, then it passes to the combustion chamber where it gets combusted and then it expands in the turbine. This turbine produces the work which is required to run the compressor, and then the rest of the enthalpy drop will take place in the nozzle. So, rest of the expansion or enthalpy drop, so the conversion to kinetic energy will take place in the nozzle and hence it produces the thrust for a engine. So, since the function of the nozzle is to have reduction in enthalpy and hence rise in kinetic energy, and that is a major component in case of turbojet engine, turbofan engine and also in ramjet engine. So, discussion about nozzle flow becomes important. So, let us start to discuss about nozzle flow and some basic about nozzle flow. Here this part will actually deal mainly with the relations about nozzle flow which are derived from the basic gas dynamics. We are not going to go in the details of gas dynamics, but we are going to touch the concept of nozzle flow through the gas dynamic relations. Let us first understand the isentropic relations. We have also derived partly those relations, but we are going to revisit them, and we know that the total temperature to static temperature relation says that the ratio is equal to 1 plus gamma minus 1 by 2 m square, and hence P naught upon P is equal to T naught upon T bracket raised to gamma upon gamma minus 1. So, it is equal to 1 plus gamma minus 1 by 2 m square bracket raised to gamma upon gamma minus 1. Similarly, stagnation to static density ratio is equal to T naught upon T bracket raised to 1 upon gamma minus 1, and hence it is 1 plus gamma minus 1 by 2 m square bracket raised to 1 upon gamma minus 1. So, these relations are isentropic relations and they are between the static and stagnation quantities. So, if we know a static quantity or total quantity, then knowing the Mach number we can calculate the other unknown thing. Here we have made an assumption of calorically perfect gas and hence gamma is constant over here for this relation. This relation will be used by us in the further studies where we will vary the Mach number and we can get different ratios. A special thing will be told or will be required is for Mach number 1 or for sonic conditions, and these relations will get transformed to very simple relation which states that T naught upon T is equal to 1 plus gamma minus 1 by 2, and this Mach m square will become 1. Similarly, P naught upon P is equal to 1 plus gamma minus 1 by 2 bracket raised to gamma upon gamma minus 1, and rho naught by rho is equal to 1 plus gamma minus 1 by 2 1 upon gamma minus 1. So, these are the isentropic relations between static and stagnation quantities for Mach number 1. Now, we will see something new, and that is for the 1D inviscid compressible flow relations. We partially know those relations. In case of incompressible flow, we state that area into velocity at the inlet of a duct is equal to area into velocity at the outlet of a duct, but that relation is for incompressible inviscid flow. But now we are going to write the expressions for mass, momentum and energy related to 1D incompressible 1D inviscid compressible flows, and as per this relation, rho into u is equal to constant, or rho 1 u1 is equal to rho 2 u2, and hence d of rho u is equal to 0. This is mass conservation equation for one dimensional case. So, it states that density into velocity, the product at station 1 if a duct is equal to the same product at station 2 in a duct. Other relation for momentum equation states that P plus rho u square is equal to constant, or P1 plus rho 1 u1 square is equal to P2 plus rho 2 u2 square, and hence in the differential form this equation is dP plus rho u du is equal to 0. This relation states that pressure plus density into velocity square at station 1 is constant, and hence it is equal to the same summation pressure plus density into velocity square at station 2. Similarly, the energy equation will be H plus u square by 2 is equal to constant. Here we are having assumption that the flow is adiabatic, there is no any heat addition. So, this says that H1 plus u1 square by 2 is equal to H2 plus u2 square by 2, and this in differential form will become dH plus u du is equal to 0, and hence this relation will be very much known to us, since we know that H1 plus u1 square by 2 is equal to H naught, which is total enthalpy in station 1, and that is equal to total enthalpy in station 2, and both the enthalpies will be same since there is no heat addition between station 1 and station 2. There is one more relation which should be known to us in the compressible flow regime, which says that acoustic speed square is equal to dP by d rho in the entropy constant state. So, we have A is equal to square root of dP by d rho at constant entropy. So, it is equal to square root of gamma RT for gases. So, this is also a known relation for 1D inviscid compressible flows. Further, these relations, as I said, are for 1D, but these relations would also be valid for quasi 1D, where quasi 1D relation by meaning it is more than 1D but less than 2D complications, where we are feeling that flow has variation only in one direction and there is minor variation in the second direction. That is what we mean in the quasi 1D case, and in case of 1D we mean that there is only variation in one direction or in the direction of flow. So, in the quasi 1D the differential form of pressure and energy is same, but the change is there in the mass conservation equation for the quasi 1D, and that is rho AU differential is equal to 0. So, we have rho 1 U1 A1 is equal to rho 2 U2 A2, and this is mass flow rate into area. This is basically kg per second mass passing through one section is equal to kg per second mass passing from the other section. Mass flux into area is equal to mass flux into area, where rho into u gives us mass flux. So, these are the isentropic relations. Having known these isentropic relations, we can further derive few relations related to the nozzle. Let us consider that there is a divergent duct, and this divergent duct has an inlet which is station 1 and an outlet which is station 2, and then we know P, rho, U and A are the properties at station 1. So, similarly P plus dP, rho plus d rho, U plus du and A plus dA are the properties at station 2, where we have infinitesimal change in area A. As per mass conservation equation, we know that d of rho AU is equal to 0 or rho UA is equal to constant. So, we know that rho 1 U1 A1 is equal to rho 2 U2 A2. We know that at station 1 we have rho U A, and at station 2 we have rho plus d rho, U plus du and A plus dA. This gives us rho AU is equal to rho plus d rho. We will multiply these two brackets, then we will get AU plus ADU plus UDA plus DU dA. But this higher order term we will neglect, and then we can multiply this and we can get rho AU is equal to rho AU plus rho ADU plus rho UDA plus AU d rho, and then we will have again some higher order terms which are A du d rho plus U dA d rho, which we will again neglect. Further, this rho AU will also get cancelled, and hence we will have rho A du is equal to rho A du plus rho U dA plus A U d rho is equal to 0. Since we know that rho AU is constant, we will divide both the sides by rho AU, and then we can get du by U plus dA by A plus d rho by rho is equal to 0. So, let us say that this is equation number 1. Now, we will use momentum equation in differential form, which says that dP plus rho u du is equal to 0. So, we have dP by rho is equal to minus u du. We can further write it like dP by d rho into d rho by rho is equal to minus u du. Suppose we are considering again isentropic case where entropy is constant, then dP by d rho is equal to a square d rho by rho is equal to minus du. We can divide this a square on other side and we can get minus u du upon a square, but we will divide and multiply by u. So, we can get minus u square upon a square into du by u. As per the definition of Mach number, we know that d rho by rho is equal to this u by a is Mach number. So, it is m square into du by u. So, this we will say as equation number 2. So, we will put equation number 2 into equation number 1 and we can get du by u plus dA by A minus m square into du by u is equal to 0. So, we have dA by A plus 1 minus m square du by u equal to 0. So, we can write dA by A is equal to m square minus 1 into du by u. So, this relation is called as area Mach number, this relation is called as area velocity relation. Now, let us understand or analyze this relation. If we try to analyze this relation, we can say that, let us say that if Mach number is less than 0, it is a minus. So, if Mach number is, let us assume that Mach number is less than 1, which is subsonic. So, if Mach number is less than 1, that would give us m square minus 1 as less than 0. So, this will be a negative number, and since this is a negative number, we will further assume that, let us say that dA is less than 0, where we mean that dA area is decreasing. So, dA is less than 0. So, we are saying that it is subsonic duct, a subsonic flow in a duct of converging cross section. So, for this case we can say that dA left hand side is negative, right hand side, since Mach number is subsonic, is also negative. So, this gives us a fact that we will have du to be positive, which is greater than 0. That means this duct is acting as nozzle. So, we have subsonic duct with converging cross section acts as nozzle. Now, if Mach number is still less than 1, flow is still subsonic. So, we still have m square minus 1 less than 0, but now let us assume that dA is greater than 0. So, what we are talking about is subsonic flow in a duct of diverging cross section. If we are talking about such, then this dA is positive, which is left hand side is positive, but right hand side says that it is negative, since m square minus 1 is negative, but right hand side also has to be positive since dA is positive. So, du has to be negative, then this m square minus 1 is negative, du is negative. So, then this product will become positive, which states that it acts as diffuser. By the definition, nozzle is the entity which increases the kinetic energy at the expense of enthalpy drop, and diffuser is the entity which decreases kinetic energy at the expense and rises the enthalpy. So, we have diverging cross section acting as diffuser for subsonic flow. We will write down this relation again, which states that dA by A is equal to m square minus 1 into du by u. Now, if we have Mach number greater than 1, which gives us m square minus 1 greater than 0. So, it is positive, and let us assume that dA is again greater than 0. Now we are talking about supersonic flow in a duct with diverging cross section. So, here left hand side is positive, right hand side is actually positive. So, we will get du also to be positive, and this means that supersonic flow in a diverging duct acts as nozzle. Now, let us consider fourth case where we again have m more than 1. So, m square minus 1 will again be more than 0. So, we have again one more assumption that dA less than 0. So, we are considering supersonic flow in a converging cross section. Here, since left hand side is less than 0, it is negative, right hand side bracket term is positive, but since left hand side is negative, right hand side also has to be negative. So, for that du has to be less than 0, which states that supersonic flow in a converging duct would be diffused, since supersonic duct is going to act as diffuser. So, we have basically two ducts. One is diverging duct, in the direction of flow it is diverging, and then we have one more duct which is converging in the direction of flow. So, this diverging duct will be acting as nozzle for supersonic flow, and it is going to act as diffuser for subsonic flow. This converging section will act as nozzle in subsonic flow and diffuser in supersonic flow. So, this is the judgment about the duct flow. So, we are talking about nozzle. So, we have to consider both the sections, but depends upon the flow Mach number. However, further we can have a convergent divergent duct, which is also called as CD duct, convergent divergent duct, acting as nozzle for subsonic entry and supersonic outlet. So, this is what we are calling it as the basics of flow through nozzle, where we are deriving the relation for area and Mach number. Now, flow through nozzle would have basically many kinds of complexities, and those complexities we are going to discuss here. Consider now that we are having a convergent divergent duct placed in a chamber which is attached with a vacuum tank, or which is attached with a vacuum pump, and then on one side it is attached to a reservoir which has pressure P naught and temperature T naught. The vacuum pump, we can connect the outlet of the nozzle, which is a convergent divergent duct. We are connecting to a chamber which is connected to vacuum pump, which can maintain desired pressure Pe or exit of nozzle. Now we are saying this pressure as PE. So there are many kinds of flow situations which will be governed by the pressure difference between P naught and PE. We are going to discuss those situations. As per those, we will first draw the nozzle again. Suppose this is the CD, convergent divergent duct, this is inlet, this is outlet, and we are going to plot few things for this special case, and those plots we will discuss here. So this is pressure versus X, and then we will plot later on mass flow rate. Suppose the exit pressure is PE and the inlet pressure is P naught. And to start with, in our experiment, PE is equal to P naught, and then that is what it leads to. So let us say mass flow rate and then exit pressure by P naught ratio, and this is suppose 1. So PE is equal to P naught. So for this particular case, there will not be any flow through the nozzle or duct, but now we will decrease the value of the exit pressure, and that decrement in the value of the exit pressure would give, this is the value of P naught, and we were talking about value of PE is equal to P naught. So this would be a straight line, constant pressure in the complete duct. So there is no mass flow rate in the duct. Now we decrease the exit pressure. Since we are decreasing the exit pressure, there will be fluid which is coming out from the reservoir side. It will decrease the pressure since flow rate is very small, velocities are very small, and we know that subsonic flow will be getting enthalpy drop and increment in velocity in the convergent duct. So convergent duct act as nozzle for the subsonic flow, but it will get minimum pressure and maximum Mach number at the minimum cross section. Then this is the diverging duct. So diverging duct for subsonic flow will act as diffuser, and it increases the pressure. This will continue for few exit pressures. So there are many solutions possible as what we increase the mass flow rate by decreasing the exit pressures. So for every exit pressure value there is a solution. However, for a particular exit pressure, the flow will become Mach number 1 at the minimum cross section. So flow reaching Mach number 1 is a attainment of sonic state at the minimum cross section, and hence the minimum cross section here onwards would be considered as the throat, since it has Mach number 1. There onwards, for the first instance this pressure will increase, but for latter any decrement in exit pressure below this particular value, which was leading to P star, which is the Mach 1 pressure, any pressure would not alter the pressure profile in the convergent portion, since for any exit pressure value there is unique variation for the convergent duct, and then it will reach subsonic state. It will be in subsonic state throughout the convergent duct, reach the sonic state, and then it will try to further expand. But if it continues to expand, then it will reach a state in the exit which is not equal to the exit pressure, which is much below. So for that all sake there will be a shock and this shock increases the pressure and then will make the flow to be subsonic at this location of appearance of shock. So, for further onwards the subsonic flow encounters the divergent duct and acts as diffuser. But for a particular exit pressure value, the flow continues to expand and attains the exit pressure isentropically. So, that matching is what the matched exit pressure corresponding to the outlet pressure. In this, before this and the case where we had attained sonic condition at the throat, this region is called as over expanded region. Further, here onwards if we decrease the pressure, then it is called as under expanded, since the nozzle does not give sufficient expansion to the flow, and at the exit of the nozzle we still have flow expansion possible, since the pressure at the exit is higher than the pressure of the chamber which is attained from the vacuum pump. In this case, if we try to plot the mass flow rate, then mass flow rate is initially increasing as we decrease the exit pressure, and for the exit pressure in which we have attained Mach 1 for the minimum cross section, there mass flow rate becomes maximum, but it does not change for any further decrement in mass flow exit pressure, and then that is what we are calling it as choking condition. So, for a particular value of exit pressure we will attain Mach number 1 in the minimum cross section, and for that case we will attain the maximum mass flow rate, beyond which when we decrease the pressure at the exit there will not be any decrement in mass flow rate and mass flow rate becomes constant, and this constancy in Mach number should also be correlated with no change in the subsonic pressure plot, subsonic region pressure plot or Mach number plot, since there is unique solution for the exit pressure of any value at the exit for the given P naught and given T naught. So, this is what we refer as the nozzle flow through a convergent divergent duct. Now, we will try to find out what is the choked mass flow rate. Choked mass flow rate is suppose m dot. So, it is equal to rho star u star into A star, where star quantities refer to the sonic conditions which has been attained at the minimum cross section. We also know that from our area Mach number relation, we also know that for Mach number 1 the term in the bracket will be 0. So, this right hand side will become 0. So, we mean that dA is equal to 0. So, it means that Mach number 1 will be always attained at the minimum cross section. So, if we are considering convergent duct, then convergent duct will reach sonic condition at the exit for a particular pressure difference. Similarly, if there is convergent divergent duct, then this duct will have sonic condition in the minimum cross section. Having said this, we can write down m dot is equal to rho star upon rho naught into rho naught into u star into A star. But we know rho star upon rho naught from the Mach number isentropic relations, which is 1 plus gamma minus 1 by 2 bracket raised to minus 1 upon gamma minus 1. The relation was stating that rho star rho naught upon rho star is equal to 1 plus gamma minus 1 by 2 bracket raised to 1 upon gamma minus 1. So, the same relation is put over here is equal to rho naught. We have u star is the velocity at sonic condition. So, but at sonic condition we have Mach number 1. So, velocity is equal to speed of sound, which is A star small a star into capital A star. But we know A star is equal to under root gamma r T star. So, we can write down m dot is equal to 1 plus gamma minus 1 by 2 raised to minus 1 upon gamma minus 1 into rho naught into gamma r T star into A star. So, we have m dot is equal to 1 plus gamma minus 1 by 2 bracket raised to minus 1 upon gamma minus 1. Rho naught we can replace by P naught upon R T naught, and here we can write down T star as T star upon T naught into T naught into A star. So, we have 1 plus gamma minus 1 by 2 minus 1 upon gamma minus 1. So, we can write down, we can actually have this r into square root and this T naught into square root. So, which we can write down as P naught upon square root of T naught into square root of gamma by r into, then this term is remained, which is T star upon T naught square root, and we know it is equal to 1 plus gamma minus 1 by 2 bracket raised to minus half, and then we have A star. Here we are using the relation which is T naught upon T star is equal to 1 plus gamma minus 1 by 2. So, we have m dot is equal to P naught upon square root of T naught into under root gamma by r into 1 plus gamma minus 1 by 2 bracket raised to minus gamma plus 1 divided by 2 into gamma minus 1 into A star. So, when we have choking condition, then we can find out the mass flow rate using this relation, where A star is the area at the minimum cross section or the throat, and P naught and T naught are the total conditions corresponding to reservoir, where we need the values of gamma, which is specific heat ratio, and R, which is specific gas constant. So, knowing this, we can find out mass flow rate at the exit of the nozzle. Now, we will go ahead and find out the relation, which is area Mach number relation. Here we let us consider are having a convergent divergent duct, and we are interested to find out what is the Mach number in this section, since we know the Mach number in this section. So, in the star condition we know that it is Mach number 1, and then we are interested in finding out the Mach number in section 2, in section 1, in section 3, or in any section. We know that mass flow rate is constant, we are working with steady nozzle. So, mass flow rate through the minimum cross section, which is rho star A star into U star, is equal to mass flow rate in any section other than star, which is suppose rho into A into U. So, we will have A, which is area at any section, divided by A star, which is area at the sonic state, is equal to rho star by rho into U star by U. We can further rewrite this by stating rho star upon rho naught into rho naught, and U star is equal to A star upon U. We know that rho naught upon rho star is equal to 1 plus gamma minus 1 by 2 m square bracket raised to 1 upon gamma minus 1, and there is a gas dynamic relation which says that U upon A star, which is bracket square, is equal to M star, which is bracket square, is equal to gamma minus 1 by 2 M square divided by 1 plus gamma minus 1 by 2 M square. So, this Mach number is the Mach number at the section for which area is A, and we are interested to find out this Mach number only. So, we have A upon A star, we will square this complete equation. So, we can write A upon A star square is equal to rho star upon rho naught square into rho naught upon rho square into A star upon U square. So, we have A upon A star square is equal to rho star upon rho naught square into rho naught by rho square into M star square, and we have this relation for M star. So, A upon A star square is equal to rho star upon rho naught. This relation is known to us, and we have relation also about rho naught upon rho, which is 1 plus gamma minus 1 by 2 M square bracket raised to 1 upon gamma minus 1. This relation is for any Mach number, but rho naught upon rho star relation is specific for Mach number 1. So, this M square term will cancel. So, we needed 3 relation, one relation for rho star upon rho naught, which is here, one relation for rho naught upon rho, which is here, and one relation for M star square, which is here. Putting these all relations, we can write down A upon A star bracket square is equal to 1 upon M square into 2 upon gamma plus 1 into 1 plus gamma minus 1 by 2 into M square bracket raised to gamma plus 1 upon gamma minus 1. So, we know area A in this section, we know A star in this section. So, we know left hand side. So, we will iteratively find out the Mach number which would patch or match the left hand side value, and hence we can know the Mach number for any cross section if flow is having supersonic velocity in a convergent divergent duct. This relation is also valid in the convergent section provided we have choking condition in the throat. For this relation, we will have complete isentropic flow in the complete duct. So, there has to be no shock. Having said this, we end our discussion about the nozzle flow, and now we can go ahead and solve or work with the different other components of the engine. Thank you.